All right, let's dive right in. We're going to be talking about a world that is so small it's almost impossible to imagine. The world of nanocrystals. These tiny materials have some seriously incredible potential. But here's the catch. To actually use them, we first have to understand them. We need to see their hidden architecture. Basically, we need a map. And that really is the central question, isn't it? How do you map a world that's completely invisible? I mean, we're talking about structures that are thousands upon thousands of times smaller than a single human hair. So how on earth can we possibly create a detailed 3D map of something we can't even see? You see, when you shrink materials down to this tiny nanometer scale, something amazing happens. Their properties can change completely. They might get stronger or become superconductive or develop totally new chemical abilities. But to engineer these things, to actually build with them, you have to know their atomic blueprint. You have to know what you're working with. And that brings us to this really brilliant solution. Scientists have come up with a new kind of map just for the nanoscale. They call them fringe visibility maps. And the best way to think of them is as a kind of roadmap for exploring the hidden world inside a single crystal. So to get how these maps work, we first have to talk about what they're actually mapping. When you look at a crystal with a super powerful electron microscope, you don't really see individual atoms. Instead, you see these striped patterns. They're called lattice fringes. And each set of stripes you see, that's a direct view of a specific plane of atoms inside that crystal. It's kind of like looking at the contour lines on a topographical map. Now, here's the key to turning those fringes into a map. You can only see a particular set of fringes when you're looking at the crystal from just the right angle. You tilt it just a tiny bit and poof, they're gone. Well, that specific range of angles where a set of fringes stays visible, that's called a visibility band. Think of it like a highway wrapped around a globe, a specific path of orientations where that particular atomic plane is visible to you. And hey, don't just take my word for it. The researchers who came up with this technique said it perfectly themselves. By mapping out all those different visibility bands we just talked about, they created a real, functional guide to the crystal's 3D structure, a genuine roadmap for the nanoscale. So what makes this new map such a big deal? Well, it's what's known as a direct space map, and it's a huge improvement on an older method that used something called Kikuchi maps. Now, the crucial difference, and this is a game changer, is what determines the width of those visibility bands. For these new maps, the width depends on the plane spacing divided by the crystal's thickness. This makes them absolutely perfect for thin nanocrystals. The older maps, on the other hand, depended on the microscope's electron wavelength, which made them better for thicker crystals. So this new tool really unlocked the ability to characterize these super thin nanomaterials. Okay, so we've got this awesome roadmap. How do we actually use it? Well, let's gear up and go on our first expedition, charting the 3D structure of a single, unknown nanocrystal. The protocol is surprisingly systematic, almost elegant. First, you tilt the crystal around until you see a nice, clear set of fringes. Then you lock onto that and tilt along the fringe line until a second set appears, crossing the first one. That's a cross fringe. It's like a major intersection on your map. You record the coordinates, the spacings, and then you just repeat the process, finding more intersections to build out a complete 3D model. You're literally navigating from one landmark to the next. And the result of all this is just incredibly powerful. By following this simple protocol, a researcher can take just a handful of 2D microscope images from different angles and reconstruct the particle's entire three-dimensional atomic lattice. You're making a leap from a flat picture to a full architectural blueprint. It's amazing. All right, for our second expedition, we're going to scale things up. I mean, it's great to map one crystal, but what if you want to understand an entire population of them? It turns out, this technique can be used to fingerprint a whole collection of particles at once. Here's how it works. Because the map shows you the total area of all the different visibility bands, you can actually calculate the statistical probability of seeing any given pattern in a random sample. It's kind of like using a map of a whole country to predict how likely you are to see, say, mountains versus beaches if you were just dropped in at a random point. The map tells you the odds. And this table gives you an idea of what that looks like. Don't worry about the numbers and brackets, they're just labels for different atomic planes. The key takeaway is this. For a typical crystal, you might have about a 4.6% chance of seeing a 111 fringe pattern. But the chance of seeing a 110 cross fringe, that's a tiny 0.3%. So by comparing these predicted odds to what they actually see in a sample, scientists can confirm the structure of the entire population. It's a statistical fingerprint. And using this fingerprinting method leads to some really fascinating, almost weird insights. For example, the maps predict this surprising crossover point. For particles that are bigger than about 2 nanometers, you're much more likely to see simple, single fringes. But for particles smaller than that, the more complex cross-fringe patterns actually become more common. It's totally counterintuitive, but it's a direct result of the geometry of the map. Okay, time for our final expedition. This time, we're going to use our roadmap not just for navigating, but for surveying. We can actually use it to measure the local terrain, so to speak, to measure a crystal's thickness with incredible precision. Remember how we said that a visibility band's width depends on the crystal's thickness? Well, that little detail turns out to be a really powerful measurement tool. A thicker crystal has narrower visibility bands, meaning its fringes disappear after just a small tilt. But a thinner crystal, it has wider bands, so you can tilt it much farther before the fringes vanish. So this means a scientist can literally take a crystal, find a set of fringes, and then just carefully tilt it until that pattern disappears. By measuring that precise tilt angle, they can pop it into a simple formula and calculate the crystal's exact thickness right at that spot. It is such an elegant and clever way to measure that third dimension. So this technique is already pretty amazing, right? Well, hold on, because it's about to get a major upgrade. Let's take a look at the horizon and see what the future of nanovision holds. New technologies are coming online right now that are going to make these maps exponentially more detailed and more powerful. We're talking about aberration-corrected microscopes that can get to sub-angstrom resolution. That's a resolution smaller than a single atom. And we're getting goniometers, those are the little stages that do the tilting, with just mind-blowing precision. And here is the real kicker. The researchers point out that the number of things you can do, the number of analysis strategies, the number of roads on our map, it doesn't just go up a little bit. It increases at least quadratically with resolution. So a small improvement in the microscope causes a massive explosion in the new kinds of data we can collect and the ways we can analyze these particles. So we're really moving from a fuzzy, incomplete picture of the nanoscale to having these incredibly detailed, high-resolution roadmaps, which of course leaves us with one last huge question. As these roadmaps for the nanoscale become ever more detailed, what new properties, what new materials, and what incredible new worlds will we be able to discover and ultimately to build?